today we will look into various aspects of identifying state points considering the property tables of pure substances. The best way in which this can be understood is through solution of problems, and we will consider a few problems which we will work out. So, the first problem, which is problem 1.1, is written here, described here. As per the custom, I will go through the problem description, then draw a schematic of this problem, and then we will proceed towards solving the problem. A cylinder has a thick piston initially held by a pin as shown in the figure below. The cylinder contains carbon dioxide at 150 kilopascal and at an ambient temperature of 290 Kelvin. The metal piston's density is given and the atmospheric pressure is given. The pin is now removed, allowing the piston to move, and after a while the gas returns to ambient temperature. So, you can see that there is a piston, there is a pressure imbalance across the two sides of the piston. This is the first important information from the problem. So, because there is a pressure imbalance, the piston has a tendency to either move up or down, it depends on which side pressure is more. So, to arrest the piston from moving further, there is a pin which is holding the piston. If the pin is removed, the piston will freely move and it will come to a location where it is dictated by the equilibrium of forces from all sides, which is called as mechanical equilibrium. Question is that is the piston against the stops or not? So, to work out this problem, so let us draw a schematic of this in the board. So, I will draw a schematic of this problem in the board. So, you have a pin, this is the height of the piston, h is equal to 100 millimeter. Then you have again this as 100 millimeter and this as 50 millimeter. The system here is carbon dioxide, which we show by this dotted line. So, whatever is given, let us note it down, it may help us. So, state 1, (150 kilopascal) this is P1. Okay. Now, what will be the equilibrium pressure at which the piston will float if the pin is removed? Let us calculate that. So, what is P equilibrium? P equilibrium means if the piston is in equilibrium under all forces, then what would be the corresponding pressure inside? So, for that we draw the free body diagram of the piston. free body diagram of the piston. So, this is atmospheric pressure, right. A is the area of the piston, then you have mass of the piston into g, which is the weight of the piston, and then from this side you have P equilibrium into A, right. So, if the piston is moving in a quasi equilibrium process or quasi static process, these forces are always in equilibrium. So, if the volume is changing, this is changing, but locally it is always in equilibrium, that means resultant of these forces is 0. So, we can write P equilibrium into A is equal to P 0 into A plus mg. So, P equilibrium is equal to P 0 plus mg by A. Okay. The mass of the piston you can calculate the density into volume. So, rho piston into A into H, this is the mass. So, A is not required. Density of the piston what is given? So, let us mark out these values. Density of the piston is 8000 kg per meter cube. H is 100 millimeter, that means 0.1 meter, G is 9.81 and what is P 0? P 0 is this one, P 0 is given as 101 kilopascal. So, if you substitute the values in most of the problems that I will be solving in the class, I have made some pre-calculations and I will not waste time by clicking the calculator to work this out. I will give you the value if it is available, because in thermodynamics depending on this value the solution of the problem will be there, that is why thermodynamics is so interesting. So, depending on the specific value the physics of the answer will be has to be set. It does not have a specific rule that whatever is the value the answer to the state point is unique. The answer to what is the state depends on what is the value which is coming. So, this value is very important, not that we can say that whatever is the value based on which a general answer will come. So, this value is 108.8 kilopascal. So, if this pressure is more than, so what is P1? P1 is 150 kilopascal. That means at state 1 this force in the upper direction is greater than the force in the lower direction. That means had the pin not been there the piston will have a tendency to go up. Piston wants to go up and the pin actually restrains it from doing that. Okay. Now, what happens when the pin is removed? When the pin is removed, this piston will have a tendency to go up. Question is how far will it go up, right. So, it says that the piston, the pin is now removed, allowing the piston to move, and after a while that the gas returns to ambient temperature. So, question is, does the piston hit the stops? So, hypothetically assume that the piston hits the stops. Okay. If that be the case, then the final volume will be whatever is the volume plus this much up to the stops. So, we can write P1 V1 by T1 is equal to P stop into V stop by T stop. What is the assumption? Assumption is that we can treat carbon dioxide at such low pressures as ideal gas. Remember, a real gas can be approximated as an ideal gas at reasonably low pressure or high temperature. So, assuming ideal gas behavior, what is given is that at state point 2, which is assumed to be the stop here, the gas returns to the ambient temperature. It started with the ambient temperature at, what is that, T1 is 290 Kelvin, and it is returning also to the ambient temperature. So, if it is returning to the ambient temperature and starting with the ambient temperature, then T1 is T stop, right. Remember that T1 is equal to T stop, that does not mean that the process from 1 to stop is isothermal process. It says that the piston goes to whatever, it may be stop or below the stop, and then the system is allowed to come to ambient temperature by maybe transferring heat. So, T1 is equal to T stop, but in between all the state points were not same as T1. So, an isothermal process means that all the intermediate state points will be at the same temperature, not just that the final and initial temperature are the same. So, this is a classical example where final and initial temperature are the same, but it is not an isothermal process. In between the temperature was not guaranteed to be same as T1. So, now you can calculate from here P stop is equal to P1 into V1 by V stop. Okay. So, what is V1 by V stop? V1 by V stop is 100 by 100 plus 50. So, this is 100 by 150 into what is P1 is 150. So, this is 100 kilopascal. Okay. Now, look into this equilibrium pressure. When the piston is moving, its pressure, can it fall below equilibrium pressure? The answer is no. It will move in a quasi equilibrium process, so its pressure will be equilibrium pressure. If it hits the stops, the pressure inside will build up. Why? Because it wants to go further, but the stops is preventing that. So, the pressure, the final pressure has to be greater than equal to the equilibrium pressure. It is equal to the equilibrium pressure if it is not hitting the stops, but if it is hitting the stops, the pressure will be greater than the equilibrium pressure. So, this conceptual understanding you have to develop, that in the thermodynamics that we are studying in this course, if the piston is moving, it is moving in a quasi equilibrium process. If it is moving in a quasi equilibrium process, that means the pressure here is always the equilibrium pressure. The resistance pressure is not changing, so the equilibrium pressure is also not changing. When it hits here, the pressure inside will build up. So, none of this is happening, that means actually this hypothesis is wrong. That means the piston does not hit the stops. Okay. So, that is the answer to this problem. The problem what is asked is that, is the piston against the stops? The answer is no, the piston is not against the stops. We will work out another problem. So, we will look into the next problem, problem 1.2. So, the diagram of the problem is given here, and again I will read out the problem. A cylinder is fitted with a 10 centimeter diameter piston that is restrained by a linear spring. Linear spring means the spring force is proportional to the displacement as shown in the figure below. The spring force constant is 80 kilonewton per meter and the piston initially rests on the stops with a cylinder volume of 1 liter. Now, there is a air supply line. When the air supply line is opened, the piston begins to rise because the additional air will pressurize the air from the below, and the piston which was earlier resting on the stops will experience more pressure from bottom than the top, and then it will go up. In this process, the cylinder pressure rises to 150 kilopascal. When the valve is closed, the cylinder volume is 1.5 liter and the temperature is 80 degree centigrade. Question is, what is the mass of air inside the cylinder? So, just like the previous problem, here also we will draw a schematic. So, the system is air, and then what is asked is to calculate that what is the mass of air inside when the valve is closed. So, let us try to note the property data. Diameter of the piston 10 centimeter, this is 10 into 10 to the power minus 2 meter. The spring constant is 80 kilonewton per meter. V1 is 1 liter, that is 1 into 10 to the power minus 3 meter cube. Then P equilibrium 1, the pressure at which the equilibrium pressure at which the piston starts rising is 150 kilopascal. V2 is 1.5 liter, is 1.5 into 10 to the power minus 3 meter cube, and T2 is 80 degree centigrade. Question is, what is M2? Okay. So, can you tell what is the difference between the previous problem and this problem? The difference is that because the spring force varies as the piston is moving, the equilibrium pressure also varies as the piston is moving. In the previous problem there was no spring, so equilibrium pressure remained constant. Now here the equilibrium pressure will vary. So we draw the free body diagram of the piston. So we will identify the forces. So first is, let us identify the forces due to pressure. So you have P0 into A, which is the atmospheric pressure, the pressure is P0. Here it is P equilibrium into A, and then the spring force. It is very important to figure out what is the direction of the spring force. So when the air is being supplied, the pressure here is increasing. So if the pressure here is increasing, the piston will have a tendency to go up. So the spring will give a restoring force downwards. So you have a Kx like this. So P equilibrium into A is equal to P0 into A plus Kx. So P equilibrium is equal to P0 plus Kx by A, right. So P equilibrium 2 state 2 minus P equilibrium state 1 is equal to K into x2 minus x1 by A, right, and x2 minus x1 is V2 minus V1 by A. So this becomes V2 minus V1 by A square. So what is A? A is pi d square by 4. It is a circular piston. So K is given, A is given, V2 is given, V1 is given, all these data are given. So if you calculate this, and P equilibrium 1 is also given. So this equation will give you what is P equilibrium 2. So P equilibrium 2 is equal to some value. I do not have the value with me exactly, but you can substitute all these. So P equilibrium 2 value is known.
Sir, why did you consider the weight of the piston?
So the weight of the piston here is not given. So the important question is, why don't we calculate, why don't we consider the weight of the piston, we can consider the weight of the piston and still that will not be important. So, we can add the weight of the piston, you will see that it gets cancelled out. So, actually you can consider MPG along with this. So, plus MPG so you will see that, I mean whatever is the weight of the piston, it will not matter if you find the difference in pressure. Ideally you are correct, you should consider the weight of the piston. I mean somehow I omitted that in the free body diagram, but it is very easy and straightforward to include the weight of the piston. So, if you include the weight of the piston, you have an additional term, but this P0 plus mg by A, this gets cancelled out. So, you will get P equilibrium 2. Once you get P equilibrium 2, it is very easy because M2 so P equilibrium 2 into V2 is equal to M2 R T2. What is this R? Again coming from school, students confuse. This is not the universal constant, this is the universal constant divided by molecular weight. Okay. So, this is the specific gas constant. So, this for air, what is the substance here? The air, right, this is air. So, R for air is 0.287 kilojoule per kg Kelvin. This you divide the universal constant divided by the molecular weight. Okay. So, once you do that, this is R air, this is T2. Remember that when you write this equation, this temperature has to be in Kelvin. So, this is 273.15 plus 80 Kelvin. V2 is known, P equilibrium 2 is known. So, from here you will get what is M2. The answer to this problem is M2 is 0.012 kg. Okay. So, I hope I could illustrate two very typical problems, in which one case there is a piston cylinder without spring, another case piston cylinder with spring, and how to calculate the equilibrium pressures under that condition. Let us stop here for this lecture. We will continue with other problems on properties of pure substances in the next lecture. Thank you.